My name is Max Rodriguez, and this is my third physics lab about black holes and orbits. So, a brief summary of this lab is going to first be an introduction, some of the guiding fundamental principles of physics that govern the lab, my execution, results, and then some further questions. So, the purpose of this lab was to use a computer simulation to find the mass of a black hole and a star's orbit around it. Then we tried to make a spaceship make a perfect figure eight around a planet by adjusting its initial velocity. And in the first case, our object was our black hole, and our surroundings were the star that was orbiting it. And for our computation, in both cases, we used GlowScript. So some of the fundamental principles of physics at work that govern this experiment are first the universal law of gravitation, given by f of g equals g m1 m2 over r squared. And this kind of just acts to describe the relationship between the gravitational force between the two objects that we're measuring, our system and our surroundings. Newton's second law, given by F equals ma, and the velocity and position update formula, given as seen right here. So our execution was pretty simple for this one, put all the formulas into GlowScript, then run the program, look at the results, and then we repeat that for both parts. So this was our code for part one, at least the major parts, and this was the system at the very end. So right here, as you can see, we have our system, which is our black hole, and this is the star that's orbiting the black hole. And these arrows here, they represent different forces that are acting on the star throughout its field of motion. So over here we have our v initial, which is given by this vector. It's our initial velocity, and our final velocity, which is given to a very similar vector. Our initial momentum and our final momentum, and this was used for the magnitude of the parallel force, which it's not very visible here, but there's a purple arrow that represents this. This is our change in velocity and our change in position, just given by final minus initial. Our dp dt, which is kind of just a way to rewrite the F equals ma formula, which right here it's actually exactly rewritten as that. F net equals dp dt. This code right here was used to calculate the parallel force, which is then redefined as F net parallel, and then the perpendicular force was just dp dt minus the parallel force. And then we use Newton's second law to calculate the total perpendicular force. And then down here, the mass of the black hole is given by the magnitude of the net force times the magnitude of the change in the star's position, times 2 divided by the mass of the star times gravity. That gives us the mass of our black hole, and all of our forces are given over here as such. We have the perpendicular force given by 9.28 e to the 28, our net force total, which is 9.86 e to the 28, our parallel net force, which is 3.61 e to the 28. And finally, my mass of my black hole was 1.495 e to the 34. Now for the second part of this experiment, I don't actually have an image to show on the right because I could never get it to fulfill the requirements. The requirement was that we make our space shuttle orbit a star in a perfect figure eight by just guessing through trial and error the perfect initial velocity, but I actually couldn't end up doing that because it's just really hard to guess. That's about all there is to it. There's so many factors at play. You have to basically guess the perfect initial velocity to get a perfect ellipse that would give you a figure eight. But the code for that program was over here. We have the distance from the planet to the moon, the force of the planet acting on the moon, the distance of the ship to the moon, the force of the moon acting on the ship, the planet, or the distance of the planet to the ship, and the force of the planet on the ship, the net force acting on the moon, the net force acting on the ship. And then down here we have just some constraints to apply Newton's second law. So we have the velocity of the moon, the position of the moon, velocity of the ship, and the position of the ship. Now, some possible errors were first and foremost that it was a computer simulation, which means that there was probably some factors that were not accounted for, like other stars in a nearby proximity that may have had something of a gravitational effect. And then some further questions. One we have what sets apart the resultant force, including its parallel and perpendicular components, relative to motion from the rate at which momentum changes and its corresponding components. Although they're equal in value, determining the resultant forces necessitates an awareness of every external force acting on the system, while assessing the momentum's rate of change only calls for information about how the system's velocity is altering. And then our second question was, what elements are essential in a computational model to accurately forecast the motion of a system, accounting for all interactions impacting it? And the short answer to this is everything. Literally everything in the environment that exerts an influence on the system. And that just depends on your intuition. Given whatever you're programming, you need to be able to take into account every single thing that's acting on it. But that is my presentation.